Hello, I'd like to welcome you to lecture 9 of 3N03. We'll discuss in this lecture Zener diodes and their applications in regulation and voltage limiting. And this lecture is from chapter 3 of the book of Floyd, sections 3.1 and 3.2. In the past few lectures, we discussed the diode, and we agreed that the diode has three regions of operation. The first one, when the voltage applied across it is positive, the voltage is usually zero until the diode reaches its own voltage, and then the current starts to increase. It can really take any value. This line can be a vertical line, or we can take into account the resistance, so we can have a resistance as well in series with the equivalent voltage source. But the thing is, it's effectively once it turns on, the current through it is determined by the external resistors and components of the circuit. When you apply reverse voltage, so when you make the cathode more positive than the anode, we say it is in the reverse bias, and the current is going. This current here is very small, usually very small. We simply consider it to be zero, so the diode will be open circuit until the diode reaches a region called the breakdown region. When it breaks down, then it can allow current to go from the cathode to the anode. So this is a negative current, okay? And there are some diodes that are designed to work in this area. We call these diodes Zener diodes. They are heavily doped diodes, so the impurities, you use them in the N and B regions have higher concentration. And this brings this Zener breakdown voltage closer, maybe from 30 volts, bring it closer to only 5 or 9 volts, depending on the required function of this Zener. And the Zener diode has this symbol here. This is the anode, this is the cathode, and you have this broken line here. Notice that the Zener diode is really a diode. So it does allow current to go in the forward direction when it's forward biased. So when you make the anode more positive than the cathode, current will flow from the anode to the cathode. But when you make it reverse bias, when you make this terminal more positive than this one, then current can flow in this direction only if it reaches breakdown point. And in that case, the current flowing from the cathode to the anode, which is this current, is almost, you can see, almost constant. And it's determined by the external circuit components. And this is what makes this a great regulator, because you can keep the voltage delivered to the output or the load resistor fixed at, say, 9 volts or 5 volts with very little change for a large value, for a large change in the current. Okay, so there are, when you try to draw the characteristic of the Zener diode in the breakdown region, this is the breakdown region. So they usually define this line here, or this breakdown line, through 3 points. The first one is called the knee current and knee voltage. So this point here is called the IZK, and this voltage corresponding, it's called VZK. This is the knee voltage. This is knee voltage and current. This is where the diode starts to show breakdown characteristics. So before that, it is in the reverse bias region. The current is very small. It's considered open circuit. This current, by the way, is tiny current, very little current. The knee current and voltage, VZK and IZK, is when the diode start to show breakdown characteristics. Now, there is a second point, which is IZM and VZM. So this is a certain reverse voltage, VZM, and this is a reverse current, IZM. This VZM and the IZM represent the maximum voltage and maximum current that can be applied to the diode, because at this point the current is too high, and then the Zener, once you go beyond that, the Zener will overheat and it can melt or catch fire. Okay, so this is the maximum operating point. You should not allow more current than this to flow. Usually when they refer to a Zener diode, they refer to this middle point, which they call it a test point. So if they say this is a Zener diode with value 5 volts, this means that this point here, which is in between, midway between IZK and IZM, between VZK and VZM, this is the operating point or the test point of the diode. So the voltage here is 5 volts, say, and the current going through this one will have a corresponding value. We call this one the test point. even though it is really the operating point for this diode. As I explained to you earlier, in a diode, if you take into account the slope of the characteristics of the diode, this slope effectively represents the resistance. And you can get this resistance from the data sheet of the diode. So if I give you this curve and then I ask you find for me the equivalent resistance represented by this Zener diode, what you have to see, you have to take one point here and the current and determine the corresponding voltage. One point here, the voltage, determine the corresponding current. This represents delta change in current. This represents change in voltage. If you divide this change in voltage by this change in current, will give you the dynamic impedance, the dynamic resistance that this Zener represents. Usually it is a very small number, few ohms, you can determine the point of intersection with the z-axis, with this axis here. We can call it z-axis, the voltage axis, or the reverse voltage axis. This point can be determined. This is a point at which the current is equal to 0. So simply from the equation of a line, you say that the slope is equal to y minus y minus y naught over x minus x naught. So you can simply put here x naught to be equal to 0. X here is, I will take it as I. It really depends on how we define y and x, but remember z is the ratio between voltage to current. So when the voltage was VZT, the current was IZT. When the voltage is VZ0, the current is 0. This is the point, this point here. There's no current at this point. So if you put this equation here and then you multiply both sides, you end up with this equation that gives you VZ naught if you know the impedance. And actually the impedance and Z naught are related to one another. VZ naught are related to one another. So if you know if I know the dynamic impedance, I can get VZ naught. If I know VZ naught, I can get the dynamic impedance because this is the equation of a line. Okay, so if I know the slope, of the line, which is ZZ, and I know one point on the line, then the line is completely determined. Or if I know one point on the line and the intersection with the x-axis or the v-axis here in this case, which is VZ naught and 0, then I know fully the line. So this is exactly the same thing. When we analyze Zener circuits, there are two ways of analyzing them. As we have seen in the diode case, there are several models we can use. I'm gonna here draw for you the IV characteristics of a Zener diode. In the forward region, it's really a regular diode. It can be on at 0.7, it can be on at 0. I'm gonna give you the exact value for the forward region. So this is here the voltage between the anode and the cathode, and this is the current going through. Okay. But when you apply the breakdown region, the current will be effectively 0 until we reach a certain value, and then it breaks down, and this can be maybe 5 volts. It breaks down at 5 volts. This voltage here is minus 5 volts, but we rarely mention the negative here. We say that this Zener has a breakdown voltage of 5 volts, meaning that if you make the cathode more positive than the anode by 5 volts, then you enter the breakdown region. Okay? So in that case, if you consider this line to be vertical, you ignore the slope. This represents really by a battery of value equal to the breakdown voltage, or is really the test voltage that we agreed on. We take this test voltage as the operating point of this diode. So what limits the current going through the diode? The current can be any value determined by the external resistances and so on. A more precise or more accurate or more practical model for the Zener diode takes into account the slope of the curve. So I will tell you, okay, this diode has a breakdown voltage of 5 volts, and its characteristic or its dynamic impedance or its impedance is equal to 1 ohm. In that case, I'm asking you to take into account in the breakdown region, when it reaches the breakdown region, that there is a certain slope. Of course, the slope is usually very little. This line is almost vertical, meaning that this resistance is very small. And in that case, the equation that governs the diode, either from the model, from the characteristics curve, or from this circuit, is that the voltage across the diode, Zener diode, which is between here and here, is equal to VZ naught plus IZ multiplied by ZZ here. Okay, so we need here in this case this number VZ0, which is the intersection with the voltage axis. It is this point here really. Okay, and once you know that, they say that the voltage across the diode at any point here, or the current or the voltage here, is simply equal to this voltage plus the slope multiplied by the current. And the same thing, of course, you can get it from this model here, or you can get it from this circuit. So we can take into account either this model, this is the practical model, or the other one, which is the ideal model. Okay, let's take a look at an example here. We have a circuit like this one. This circuit has a Zener diode. It has a breakdown voltage V Zener of 20 volts. It has an on voltage in the forward direction of 0 volts. Remember, this is a diode, so it can conduct in the forward direction, can allow current to go from the anode to the cathode, and in that case it represents some on voltage between the anode and the cathode. In this case it's 0 volts. We apply to this is 1 kilo ohm. We apply to this circuit this input voltage, which is really a sinusoidal voltage oscillating between 60 and minus 60 volts, and we'd like to determine the output voltage. Now, I didn't mention anything about dynamic impedance, so in that case I'm asking you to use the ideal case. So in the ideal case, the characteristics of the diode of this diode looks something like this. In the forward region, it will turn on, and here I'm taking this one, the on voltage, to be equal to 0, so it will turn on exactly on the y-axis. And in the reverse region, it does not conduct until you reach the breakdown, and the breakdown here is simply equal to 20 volts. So this diode can be operating in one of three regions. So if you apply, if this terminal is more positive than this one, meaning that the input voltage is negative, then the voltage source, or this oscillating voltage source, is trying to push current in this direction. It's trying to push current in the counterclockwise direction. It is trying to turn on this diode in the forward region. So once this terminal becomes more positive than this one, this diode will turn on. And when it turns on, the output voltage measured between these two terminals, this one here and this one here, will be 0 volts. Because as we agreed, the on voltage is equal to 0. Okay, so this whole negative region will be removed. So once you apply negative voltage, so this terminal is more positive than this one, the diode will turn on, allowing current to go through, meaning that the voltage across this diode will be equal to 0, and the output voltage is equal to 0. Now, when we apply a positive voltage, so you make this terminal more positive than this terminal, this means that this diode will be reverse biased. It's reverse biased. But it will not break down unless you reach 20 volts, unless the voltage across it reaches 20 volts. So this voltage keeps on increasing, 0, 1, 2, 3, 4, 5, 6, up to 20. And when it reaches 20, the diode will reach the breakdown region. And when it reaches the breakdown region, current will flow in this direction. Okay, so this is now the clockwise direction. And the voltage across this circuit will be equal to the Zener voltage. So this will be equal here to 20 volts. Okay, so before it reaches breakdown, there is no current going through it. There is no current. This is open circuit, and V out is equal to Vn. Once it reaches breakdown, it really acts like a battery, where the cathode has more positive polarity than the anode. So the voltage across this circuit will be equal to 20 volts. So the top part of this waveform will be removed. So once it reaches 20, it simply gets fixed at 20. Okay, so the output waveform will be, it rises from 0 up to 20, gets fixed at 20, and then it goes down to 0 again. And then for all the negative part is removed, because the diode will be on, until it reaches 20, and then it becomes positive again. It starts to follow the input, and then it reaches 20, and then gets down again. Okay, so just remember that this Zener diode can work in one of three regions. It can be in the forward region, it can be off, and it can be in the breakdown region. And each one of them has its own conditions. So as I explained in the previous slide, when the input voltage is negative, the Zener will be forward biased, meaning that the output voltage is 0. when the input voltage is between 0 and 20 volts, positive, but between 0 and 20 volts, the Zener diode will be off, and it looks like open circuit, and then the output will follow the input. When the Zener diode reaches breakdown, then the output voltage will be constant, and it's fixed at the Zener breakdown voltage, because as we agreed, once you reach the breakdown voltage, the voltage across the Zener does not change. The current going through that's changing, and this is what makes this one a great voltage regulator. Okay, so I drew for you here the input waveform. This is the input waveform oscillating between 0 and 60. This is the output waveform. For the positive part, it goes up to 20. It remains constant at 20, and then it goes down again. For the negative part of the cycle, the diode is on, so in the forward region, so it gives 0 volts, so this whole region is removed. And when the input voltage becomes positive again between 0 and 20, the diode is off, then the output is equal to the input, and then when it reaches the breakdown region, the output is fixed at 20 again, and then it goes down, and so on. It keeps on repeating itself like that. Okay, let's take a look at one more example, and I put this example there just to give you a feeling that you can have more than one diode in a circuit, and they can perform different types of functionality. So the result of this one will not be that different from the previous result, but the analysis is a little bit different. So let's see how this is gonna go. We have here a Zener diode. It has a Zener breakdown voltage of 20 volts. So you must make the cathode more positive at the end by 20 in order to enter the breakdown region. It has an on voltage of 0 volts. So if it conducts in the forward direction, then the voltage across it will be 0 volts. We have another diode here connected to this terminal. This diode has an on voltage of 0.7 volts, and because I didn't mention anything about its breakdown voltage, the breakdown voltage for this one is very high. It's a regular diode, so it's usually designed to have a very large Zener voltage breakdown, say 60 or 70 volts. So we don't worry about it here for this circuit. We simply ignore it. And we apply an input which is shown here oscillating between 60 and minus 60. We would like to determine the output V0 across this 100K resistor. So I have here 100K resistor, and I have 1K resistor. I would like to determine the output across this 100K. Well, I have to see different parts of the cycle. If the input voltage, you can see, to make this diode conduct, you must have at least 0.7 volts. So for Vn positive, if Vn is positive, but between 0 and 0.7, this diode must be off, because there isn't enough voltage to turn it on. And this diode is reverse biased but did not reach breakdown as well, so this diode is off. So it looks like the output is not connected really to anything. This is just one terminal, one wire, but there is no return current. There is no return current path. So the voltage between here and here is simply equal to 0 volts. The output is not connected to the input. So this is when you have an input voltage between 0 and 0.7. Now, if the input increases between above 0.7, but less than the voltage necessary to make this Zener breaks down, then this Zener diode is still off, but the external diode is on, and the circuit looks like the current is flowing in this branch. Okay, you can see this way, and this one is completely off. In that case, the output, the voltage across the output is equal to the input, okay, minus the 0.7 appearing here, minus the drop appearing here. But this circuit, as you can see, I selected the 100K to be way larger than 1K, meaning that this is a voltage divider. This is a voltage divider between the 1K and 100K, but most of the voltage will appear across V0. Okay, so I can simply say that the voltage appearing here across this output will be approximately equal to Vn minus 0.7. Okay, so I'm now ignoring the drop appearing across the 1K because the 1K is too small relative to the 100K. Now, if the voltage increases above 20.7 volts, then this one will reach also breakdown, okay, and then the output will be fixed at 20 volts. So this one will be on, so you have current flowing this way, you have current flowing that way, okay. This the voltage across the output will be here equal to 20 volts once you reach breakdown. Now what about the negative part of the cycle, when the voltage, the input voltage is negative? So this side is more positive than this one. You can see this diode does not allow current to go in this direction. It cannot allow current to flow this way. So the whole in the whole negative side, this is open circuit. This open circuit meaning that the input is really disconnected from the output and the output becomes zero. Okay? So the only difference between this circuit and the previous circuit is that when it conducts in the beginning, the output is equal to the input minus 0.7 until you reach breakdown, and in that case the output will be equal to 20 volts. Okay, the output is fixed at 20 volts. For the negative part, the negative part is completely removed here because this diode will be off. You cannot allow any current to flow in this way or that way because this one looks like open circuit. So in this negative part, this diode is open circuit. The output is completely disconnected from the input, and V naught is equal to 0. So this summarizes what I have said. First, the small diode will turn on. Below 0.7, both of them are off. The output is equal to 0. When the diode turns on, but the Zener is not breakdown yet, then the output is effectively equal to the input minus 0.7. When the Zener reaches breakdown, then the output will be fixed at 20 volts. So the output from this circuit looks similar somehow to the one that we had earlier, but remember this one here, the one that we had over there was starting from 0. The output was following the input from 0, but here it will start to follow the input. The output is equal to the input minus 0.7 until the Zener reaches breakdown. Then the voltage will be constant at 20, and then when it drops again, the output will be equal to the input minus 0.7. And then when you have negative input, then the small diode will be off, and then the output is disconnected from the input, and then the output will be 0, and then it repeats itself. So it looks like a similar waveform, but there is a little bit of shift of 0.7 due to the diode voltage.